Okay, today let's talk about improper integral. Now, how can you determine that the given integral is an improper? Notice that we must inspect that our lower and upper limit of integration has an infinity value. So in this case, we have here our upper limit has bounded by an infinity. So if we have a graph here and having a function which is the y or f of x, from the definition of the definite integral, we can get the area bounded by this curve by getting its lower and upper limits. In this case, in our first case, we have here our lower limit is equal to a, and our upper limit is bounded to the infinity, to the positive infinity. Thus, that is our b. So we can get the area under the curve by applying the integration, but we are evaluating in terms with infinity. So we will be using our knowledge in the limits at infinity, where in this case b approaches to positive infinity. So in the next case, the lower limit of integration has an infinity. So our graph, we have here f of x that is bounded by the upper limits of integration, that is b, and it is bounded to the infinity, to the negative infinity, and that is our a. So taking its limit as a approaches to negative infinity, then the next case, or the last case, if both of our lower and upper limits of integration has infinity. How do we solve this integral having our upper and lower limits has an infinity? So notice that if we have a graph here that is y or f of x, and it is bounded to the positive infinity and bounded to the negative infinity, we can get the area under this curve by dividing the curve into two parts. So dividing into two parts, we have this one. So it passes through a line that is L, and we get the integration by adding these two areas, dx, where our first area has the limits of integration from negative infinity to L, and the second limit is coming from L to positive infinity. We have here our equation that is equal to the area 1 plus the area 2. So we have here our area 1 is the limit as a approaches to negative infinity, having its limits of integration that is passing from a to L. F of x dx plus the second area that is limit as b approaches to positive infinity, having our limits of integration as L passes through, as limits of integration coming from L to positive infinity, that is b. F of x dx. Now notice to our general formula, we have the value of our L is equal to 0. We can use this general formula if our graph is passing to our origin 0. Also, we can also use this formula. We can also use this formula if it passing through at any points. But in general, we will be using 0, as 0 result to a simpler reduction of the equation. If the resulting limits exist, that is L, then the resulting integrals are said to be convergent. If the resulting limits does not exist, that is positive or negative infinity, then the resulting integrals are said to be divergent. Recall on our limits at infinity, we have here the following importance theorem to be remembered for, in order for us to properly evaluate the improper integrals. So you can take a screenshot of this to make this as your note. Okay, moving to our examples, we have here the integral of sine x dx, that is from -2 to positive infinity. Feel free to pause this video and answer it on your own. Okay, to solve this equation, notice that our upper limits of integration has an infinity value. Thus, assigning this equal to b, we have our equation that is related to the case 1 is limit as b approaches to positive infinity. Thus, our limits of integration is -2 to b, and our integrand is sine x dx. Simply, by applying the integration, we have the integral of sine x is equal to negative cosine x. So our resulting equation will become negative L limit of b approaches to positive infinity as cosine x, that is integrated from -2 to b. So you will notice, where is the negative sign here? I place it outside the limit in order for us to properly evaluate the function. Okay. Next, by substituting these limits of integration to our resulting equation, it will become the negative limit as b approaches to positive infinity. We have here cosine of b minus the cosine of -2. So applying the limits in each term, we have the limit of cosine b as b approaches to positive infinity will result to an infinity value. And if we evaluate the limit of a constant, is still a constant. So our resulting equation will become the negative infinity, because of this negative multiplied by infinity is negative infinity, and negative cosine of -2 is equivalent to negative cosine 2, because cosine is an even function. If it is evaluated from any negative values, still it has a positive value. Thus, it will become negative cosine of 2. Notice that the infinite value minus a constant is still an infinite, so it is equal to negative infinity. Thus, the improper integral is a divergent. We have here our second example. Feel free to pause this video and answer it on your own. Okay, notice that our upper limits of integration has infinity. Thus, assigning this as our b, we have our limits as b approaches to positive infinity. Integrated from, we have here 0 to b as x multiplied by e raised to negative x dx. Before we take the limits of our integral, we must first evaluate our integral. Thus, evaluating first the integral, notice that we can solve this by using integration by parts. So, we let u is equal to x and du is equivalent to dx. Now, important note that in selecting the differentiation of our term, we must select the term that if we take its derivative will result to a simpler term. That is, in this case we use x because the derivative of x is just simply dx. And let dv is equal to e raised to negative x dx. Now, integrating both sides, we have v is equivalent to negative e raised to negative x. Now, using the formula of integration by parts, where the integral of u dv is equivalent to uv minus v du, the integral of v du. So we have here u is x multiplied by v, that is negative x e raised to negative x. Now, minus the integral of v, which is negative. So negative multiplied by negative is just a positive. So we can change this sign as positive. Now the integral of v du is equal to e raised to negative x dx. So evaluating this, we have negative x e raised to negative x minus e raised to negative x plus c. So we have here now that our improper integral is equal to the limit as b approaches to positive infinity. Copy this one, omitting c since we are evaluating at a definite integral. So we have negative x e raised to negative x minus e negative x integrated from 0 to b. Now, applying our limits of integration into our resulting function will become limit b as b approaches to positive infinity is equal to, we have b here, so negative b e raised to negative b minus e raised to negative b minus the values of 0, which is negative 0 multiplied by a constant, still a 0, so this will become 0, and minus e raised to negative 0 is simply is equal to 1. Now if we apply the limits in each term, notice that the limit as b approaches to positive infinity will become negative infinity here. Thus this e approaches to negative infinity is simply 0. You can try it in your calculator by inputting e raised to negative 1000. This will have a resulting value of 0. Thus 0 multiplied by negative infinity is equal to 0. Now our resulting function, value of our integral, we have this term will become 0, thus 0 then minus multiplied by negative 1 is positive 1. So we have 1 here. Thus our limit exists and it is a convergent. Okay, we have here another example Feel free to pause this video and answer it on your own. So notice that our lower limits of integration has an infinity value. We assign this as our a. So the resulting function will become the limit as a approaches to negative infinity, as our limits of integration is coming from a to 2, and our integrand is equivalent to 4 minus x negative 2 dx. Now you will question why it is negative 2. You can apply here the laws of exponent. Okay, now we must evaluate our integrand, letting the parenthesis value as u is equivalent to 4 minus x. Taking the derivative, we have du is equivalent to negative dx. Simply, our dx is equivalent to negative du. So, substituting our function, we have the limit as a approaches to negative infinity multiplied by the integral of u raised to negative 2 times dx, which is negative du, evaluated from a to. Now, applying the integration of the exponent will become, our exponent here is negative 2, adding 1 will have negative 1. Taking its reciprocal is simply negative 1. So we have here the limit as a approaches negative infinity. We have our existing negative here, and our multiplied the reciprocal of the term to the whole term will become positive. So the resulting integral of this equation, this function, will result to have a u raised to negative 1, evaluated from a to 2. Substituting our u here, that is equal to 4 minus x. Substituting our u, our u will become 1 over 4 minus x. Evaluating each term of our lower and upper limits of integration, will have the limit as a approaches to negative infinity, evaluated from 2, which is 1 over 4 minus 2, minus the term of all the values of a, which is 1 over 4 minus a. This become 1/2. And applying the limits of each term, the limit of a constant is still a constant, so it is 1/2, and the limit of 1 over 4 minus negative infinity is equivalent to 1 over 4 plus infinity. Now, adding an infinity is still an infinity, thus 1 over infinity, and applying the limits, it as 1 divided by infinity is equal to 0. Thus, this term will become 0. Now, the integral is equal to 1/2. Thus, it is a convergent. Okay, we have here another example, that is the integral of 1 over square root of 3 minus x dx, evaluated from negative infinity to 0. Feel free to pause this video and answer. Okay, notice that our lower limit has an infinity. Thus, assigning this as our a, we have here now the limit as a approaches to negative infinity, the integral of 1 over 3 minus x, which is equivalent to 3 minus x raised to negative 1/2 dx, evaluated from a to 0. We can apply here the integration by substitution, but we can also use a shortcut where we can look this and take its derivative, which is equivalent to negative dx. Thus, we have here the limit a approaches to negative infinity multiplied by a negative, and applying the integration of a power, so negative 1/2 plus 1 is simply 1/2. 2 times 1 is 2, plus negative 1 is 1, so 1/2. Taking the reciprocal of this, 1/1/2 is equivalent to 2. Thus, you multiply this to the whole term of the integral. So we have here 2 and our value of 3 minus x. Now this will become our new power, that is 1/2, evaluated from a to 0. Thus, we have limit as a approaches to negative infinity, evaluated from negative 2. We take the outside of 2 since it is common factor of this term. We'll have 3 minus 0 raised to 1/2 minus 3 minus a raised to 1/2. Now applying the limits on each term, this will become 3 raised to 1/2, and 3 minus an infinity or positive infinity is still an infinity. Thus this will become infinity multiplied by negative, so it will become negative infinity, and multiplied by a negative 2, thus this will result to positive infinity. Now we have the resulting function negative 2 cube square root of 3 plus infinity. Now notice in adding an infinite larger number to a negative still result to positive infinity. Thus our limit does not exist. Therefore this is a divergent. Okay, we have our next example, which is the integral of x e raised to negative x squared dx integrated from negative infinity to positive infinity. Now feel free to pause this video and answer it on your own. Okay, notice that this value has infinity, thus it assigned this as a, assigned also this b, will become the limit as a approaches to negative infinity, where our limits of integration is coming from a to 0, x e negative x squared dx, plus our second limit, which is b approaches to positive infinity, where our limits of integration is coming from 0 to b and x e negative x squared dx. Now this is a bit complicated, but notice that they have the same integral, so we must first evaluate the integral. So evaluating first our integral, applying integration by substitution, we let u is equal to negative x squared. And taking its derivative, we have du is equal to negative 2x dx. Now our dx is equivalent to negative du over 2x. So we use these terms in our integral. We have x e raised to negative x squared dx, so it is equal to the integral of x, where our power of e is used by substitution, which is u, which is equal to e raised to u, where our dx is equivalent to negative du over 2x. So you can cancel out the x here, and we have a constant of negative 1/2, because we have here negative 1/2 integral of e raised to u du. Now the integral of e raised to u is simply e raised to u. So we will have negative 1/2 multiplied by e raised to u, which is e raised to negative x squared. So our resulting function should be looked like this. Applying the limits of integration on each term, we'll have, notice we have a common here, so it is negative 1/2 limit of a raised to negative infinity. Limit as a approaches to negative infinity. Substituting, we have e raised to negative x squared, which is u, minus e raised to negative a squared. Since it has a negative, since our constant here is negative 1/2, so take it outside, we have negative 1/2 the limit of b approaches to positive infinity as e evaluated from negative b squared minus e raised to 0. Notice that e raised to 0 is simply equal to 1. And applying our limits on each term, the limit of e raised to negative a squared, which is our a here is negative infinity, is just an infinity. So applying our limits at infinity, this will become equal to 0. Same as with this one. Now, from simplifying our equation, we have negative 1/2 here, negative 1/2, and this one, so become negative 1/2, and we have here 1 minus 0, and we have here 0 minus 1. But we have here 0 minus 1, and since it is negative 1/2, but we take this negative 1/2 outside, so the resulting so it will become negative 1. So 1 minus 1 is 0, and 0 multiplied by negative 1/2 is 0. Now this is a convergent. Moving to our last example, feel free to pause this video and answer it on your own. So we have here limit as a approaches negative infinity, evaluated from a to 0, which is dx all over x squared plus 6x plus 12. And our second limit, that is limit as b approaches to positive infinity, evaluated from 0 to b, dx over x squared plus 6x plus 12. Now we must evaluate first our integrand. Thus evaluating our integrand, this will become dx over x squared plus 6x. By using completing the square, we have x squared plus 6x plus 9. Where do I get that 9? Well, this is get by 6 divided by 2, which is 3, and raise it into squared, we'll have 9. So, notice in our original function have a value of 12. Now, what is lacking here at 9? So it lacks of a positive 3. So we'll have dx over x plus 3 squared plus square root of 3 squared. This factors came from x squared plus 6x plus 9. Notice that our integral is just an inverse function, where the integral of du over u squared plus a squared is simply equal to 1 over a, the inverse tangent of u over a. So applying this, we'll have, since our u here is x plus 3, and the derivative of x plus 3 is simply dx, so it is equal to 1, then it is equal to 1 over a, where our a here is square root of 3, 1 over square root of 3, multiplied by arc tan, or the inverse tangent, multiplied by our u, which is x plus 3, over square root of 3. So our resulting function should be looked like this. Notice in our term, it has a common factor, which is 1 over square root of 3. So we can simply take it at outside as 1 over square root of 3 multiplied by each of the limits. As a approaches to negative infinity, which is, that is evaluated from arc tan 0 plus 3 is 3 over square root of 3 minus the arc tangent of a plus 3 over square root of 3 plus the second limit as b approaches to positive infinity, that is evaluated from arc tan b plus 3 over square root of 3 minus arc tan 0 plus 3 is 3 over square root of 3. Setting your calculator into radian mode and inputting the inverse tangent of 3 over square root of 3 will give you a result of 1/3 pi. This will become pi over third. This will become pi over third. Notice that the limit, applying the limit to our variable here, the limit of negative infinity plus 3 is simply negative infinity over square root of 3, and this is equal negative pi over 2. This will become, evaluating the b as b approaches to positive infinity, this will become closer to the 90 degrees, which is equivalent to pi over 2. Simplifying our equation, we'll have pi over 3 minus multiplied by negative pi halves, it is positive pi halves, plus pi halves minus pi cube, pi third. Notice this will become 0, this will cancel out. Now our remaining value will become 1 over square root of 3. Pi halves plus pi halves is simply pi, because simply will become 2 pi over 2, so it will become pi. So multiplied with this, so this will equal to pi over square root of 3. Thus it is a convergent. That's all. Thank you.